Welcome back. In today's lesson, we'll take a closer look at how Modbus RTU handles addressing. This is how the master knows where to read or write data, and how it identifies the exact register or value it wants to interact with, whether it's getting a sensor reading or updating a configuration setting. Let's go over what we'll be covering today. We'll begin with the different Modbus register types to understand how memory is organized in the protocol. Then we'll review typical address ranges used for each type. Next, we'll explain the difference between logical and PDU addresses. We'll also cover how register offsets work when forming requests. Finally, we'll walk through a real example to see it all in action. By the end, you'll have a clear understanding of how Modbus RTU addressing works, both in documentation and in actual Modbus communication. Okay, let's take a look at the different Modbus register types. There are 4 main types, each with a specific role in how devices communicate over the network. Coils are binary outputs that can be turned on or off by the master. These are typically used to control actuators like motors or valves. The master can both read their current state and write new values. Discrete inputs are binary inputs, read only from the master's perspective. They provide status feedback, such as the state of a switch or an alarm. In our case, we'll use discrete inputs to track alarm conditions for VOC index, temperature, and humidity, helping us monitor when environmental thresholds are exceeded. Input registers are 16-bit read-only values used to hold sensor data or analog input. In our application, these registers store real-time readings like temperature, humidity, and VOC index, as well as the number of times each alarm has been triggered. Holding registers are also 16-bit, but unlike input registers, they can be both read and written by the master. We'll use holding registers to configure things like sampling intervals and alarm thresholds for each environmental parameter. Each register type serves a different role in the Modbus ecosystem, and not every device supports all 4. In fact, many devices use just holding registers or a combination of holding and input registers. It depends on the manufacturer and the application. Okay, now that we've gone over the different Modbus registers, let's take a closer look at how their address ranges are organized. This table shows the standard layout used for each register type. While manufacturers may vary, these ranges reflect the classic structure you'll often find in Modbus documentation. Coils start at address 1 and go up to just under 10,000. Each address represents a single bit that can be read or written. Discrete inputs begin at 10,001 and continue through the 19,000s. These are read-only and represent digital input states. Input registers fall within the 30,000 range. They're 16-bit read-only values commonly used for sensor data, and holding registers span the 40,000s. Also 16-bit, but they can be both read and written by the master. I should mention that the full valid Modbus address range is from 0 to 65,535, but these classic ranges are still widely used in documentation. Also, the prefixes like 1, 3, and 4 are not actually part of the message. They just help us identify which memory area the register belongs to. And as we'll see soon, these ranges tie directly into how offsets are used when building requests. Next, we're going to discuss an important distinction between logical addresses and PDU addresses in Modbus. Logical addresses are what you'll commonly find in documentation, user manuals, and Modbus memory maps provided by vendors. As we saw in the table, they include prefixes like 4 for holding registers or 3 for input registers, making it easy to identify the register type and navigate vendor-specific Modbus maps. PDU addresses, however, are what actually gets sent during communication over the Modbus network. The prefix isn't part of the transmitted address. Instead, the PDU address is derived from the logical address by subtracting an offset, with the PDU addresses starting from 0. For instance, the logical address 40,016 is represented as 15 in the PDU, calculated by subtracting the offset of 40,001. According to modbus.org, the offsets, or pre-mapping, between the Modbus data model and the device application is totally vendor device specific. This means manufacturers can have slight variations in how logical addresses are organized and mapped to PDUs, making it important to understand each vendor's conventions. In short, logical addresses are what you'll use for reference, but actual communication on the wire relies on PDU addresses. To make this clearer, let's look at another quick example to further explain how these register offsets work. So for example, if your documentation says to read holding register 4014, the Modbus request will actually use address 13 because we subtract the starting offset of 4001. This same idea applies to all register types. Each type starts at a different offset, which we subtract to get the PDU address used in communication. As shown in the table, for coils subtract 1, for discrete inputs subtract 1001, for input registers subtract 3001, and for holding registers subtract 4001. These starting values can vary between vendors, but the concept is always the same. Logical addresses are used for reference, and PDU addresses are what actually get transmitted. Once you get used to this pattern, converting logical addresses into PDU addresses becomes second nature. Okay, now let's walk through the same example in more detail. In this case, the Modbus master is sending a request to read holding register 4014 from a slave device with address 7. So let's break it down. 7 is the slave address, identifying which device should respond. 3 is the function code. Here it tells the slave we want to read holding registers. D is the register address. This is the PDU address, calculated from the logical address 4014 by subtracting the 4001 offset, giving us 13, or D in hex. 1 is the number of registers. The request is to read just 1. CRC is the cyclic redundancy check, 2 bytes for error detection. This is what actually gets transmitted. Each field ensures the request is understood and handled correctly by the slave. If everything is valid, the slave will respond with the requested data or return an error response if needed. Okay, so next we'll take a look at Modbus function codes. These codes act as instructions, telling the slave exactly what the master wants to do: read data, write data, or perform other operations. So see you in the next lesson, where we'll dig into how each function code works.